Hello, and welcome to Cable Fault Locating on Underground Medium Voltage Cables. My name is Tom Sandry, and I'm the Director of Technical Support here at ProTech Equipment Resources, and I will be conducting today's presentation. Before moving into and discussing cable fault locating and the various techniques associated with cable fault locating, perhaps a good place to start is by first examining cables and particularly the cable components. The power cable market can be segmented into three areas based on voltage class. The medium voltage class, which is 6 to 69 kV typically. The high voltage, which is 69 to 150 kV. And then the extra high voltage cable class, which is greater than 150 kV. The medium voltage cable dominates the underground cable market segment. Insulated power cables are used for transmission and distribution of electricity for various underground applications, residential as well as residential. In a typical medium voltage cable, copper or aluminum wires, either stranded or solid, are used as the conductors. These conductors are covered with an extruded polymeric stress control layer made of semiconductive compounds, often referred to as the permashield, or also known as the strand shield or conductor shield. The insulation layer immediately surrounds and is fully bonded with the conductor shield. An insulation shield encases the insulation and in some cases may be composed of the same semiconductive material as the conductor shield. The copper neutral wires are wound around the insulation shield and are usually covered with a thermoplastic polyethylene jacket for mechanical protection from the external environment and also to reduce moisture intrusion into the cable, all of which can cause a premature cable failure. There are two basic categories for cables, the extruded dielectric and the laminated dielectric. The extruded dielectric can be made up of the cross-link polyethylene or XLPE, also the PE or polyethylene class cables are examples of extruded dielectrics, and also the EPR or ethylene propylene rubber would be another form of an extruded style dielectric. Paper insulated lead covered or PILC would be an example of a laminated cable structure. Talking a little bit about cable and cable aging brings us on to the topic of an event called treeing. Now, water tree degradation is a major problem for medium voltage extruded dielectric cables, particularly service-aged polyethylene and cross-link polyethylene cables. It is perhaps the worst degradation process of a polymeric insulation that contributes to the failure of the cable. Water trees are formed and grow in the presence of moisture, impurities, or contamination and electric field over time. There are generally two types of water trees, namely the bow tie and the vented tree. Over here we can see an example of a bow tie tree, and over in this picture here we can see various examples of the vented trees. Now, bow tie trees are water trees that grow from the insulation outward toward the surfaces of the insulation. These trees grow in the direction of the electric field and will grow in both directions toward the two electrodes. Bow tie trees have a faster initial growth rate as compared to the vented trees. However, the bow tie tree is not capable of growing large enough in size and usually does not grow to a size significant enough to cause failure in the insulation. The vented trees, however, these grow from the surface of the polymer inwards toward the insulation system. These trees will grow in the direction of the electric field. The vented trees have a lower initial growth rate as compared to the bow tie tree. However, these trees are capable of growing right through the entire insulation thickness, as we can see over here. So the vented tree is definitely the more problematic of the treeing events, and these are the ones that will basically lead to cable breakdown or cable failure in service-aged cable structures. Now, in the case of extruded dielectric cables, the treeing results from water ingress and is referred to as a water tree. In laminated cables, the most common cause of treeing events is from the drying of the oil and then the burning of the insulating papers. This burning of the insulating paper leaves behind carbon deposits. Therefore, the type of tree that you would commonly find in a laminated cable structure is normally referred to as a carbon tree. Or in essence, as we can see, as the paper burns, the carbon deposits formed. Over time, the burning of the paper and the formation of the carbon deposits will again form a conductive path through the dielectric material, and in essence will lead to cable breakdown or failure. As we introduce to the cable fault locating techniques, the one thing we need to be aware of is that there are more than one technique, and there is definitely more than one tool of the trade when dealing with underground cable faults, particularly on a wide variety of faults and wide variety of underground cables. Now, what we need to understand is that even with the proper equipment and experience, cable fault locating can present challenges. These challenges are minimized significantly by understanding the equipment and techniques available, and perhaps most importantly, adhering to a disciplined step-by-step procedure. Most cable fault locating failures and wasted time can be attributed to technicians not properly interpreting the test results and then selecting the wrong tool for the job. And ultimately, a lot of wasted time can be attributed to taking a shortcut in the process. Now, education and experience in cable fault locating will help correct the or make improvements in interpreting of the results, and definitely will help correct and make improvements in the selection of which equipment and technique is best suited for a job. But only discipline is going to correct wasted time that is afforded through taking shortcuts. Now, once we understand the basic mechanics of a cable fault, we can then begin to explore the various fault locating techniques, along with the advantages and the limitations of those various techniques. And that's really what the heart and soul of this presentation is going to delve into, is learning the mechanics of a fault and learning how to select a technique or a piece of test equipment appropriate for the job. Now, one of the oldest techniques that is out there is a technique called the capacitive discharge, or a lot of people in the industry refer to it as thumping a cable. Now, this is one of the oldest techniques. In application, it is actually very straightforward and simple. We start with a device called a thumper or capacitive discharge unit. This device, in essence, creates a high voltage surge which is launched out onto the faulted cable, and this surge of energy will travel along the cable conductor, and if it reaches an area of dielectric breakdown or a failure in the insulating material, this energy that is transmitted will in essence discharge through the gap at the fault and discharge all of the energy through the faulted insulation, and all the fault current will then come back through the neutral or shield on the cable back into the capacitive discharge unit, and then will be dissipated safely to earth potential. Now, if we send a several thousand volt surge into this cable and we discharge all that energy through the gap or fault, that's going to cause a small explosion. And buried in the ground, this small explosion will cause a percussion and sound wave to travel up through the layers of earth, and you can actually then hear it on the surface of the ground. It'll actually sound, as the nickname implies, thump, 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 hence the name Thumper. Take a look at how the technique works. Again, the blue ball represents the high voltage surge of energy being discharged from the capacitive discharge unit. It is a traveling wave and will travel along the cable under test. And when the fault or gap breaks down, the energy is discharged, causing an acoustic wave traveling to the surface, and then we walk along the surface of the ground listening for this discharge or thumping sound. And that's how we would locate or find the defect in the underground cable. Very good technique, but as you can potentially see, some limitations. Can be relatively time consuming, particularly on very long cable stretches. And since we are sending high voltage surges, can be a little bit stressful to a service age cable. Another technique that has been in the industry for many, many years is a technique known as time domain reflectometry, or sometimes just referred to as TDR. Now, key note is time domain reflectometry actually is made up of several subtle techniques, one of which is called the pulse echo, arc reflection, and also impulse current are all different styles of time domain reflectometry. Many times, when we hear the name TDR or time domain reflectometry, many of us associate it with this technique here, pulse echo. But we will learn through this presentation that there are actually some subtle variations, and all of these different variations, impulse current, arc reflection, and pulse echo, all are time domain reflectometry techniques. Starting first with the pulse echo technique. The pulse echo technique is performed with a device called a time domain reflectometer, or TDR. This device will actually serve two purposes. It is a transmitter. It will actually transmit a low voltage, high frequency pulse onto a cable. This low voltage, high frequency pulse of energy will travel along the surface of the cable until it encounters some type of disruption, or more correct, a change within the characteristic impedance of the cable. Depending upon the magnitude of the impedance change, either part or all of the transmitted energy will reflect and will travel back to the time domain reflectometer. So in essence, this now becomes both a transmitter and a receiver. We have a graphical display, much like an oscilloscope, which will actually show these events. It will show the launch pulse, or the energy being transmitted onto the cable, and it will show any reflections that have occurred along the transmission path. Kind of demonstrate, we see the blue pulse representing the energy leaving the time domain reflectometer, or pulse echo, and then we have the red and the yellow pulses, which represent reflections caused by changes within the impedance structure of the cable. The red, we show kind of a partial open in the cable, but again, we still have some continuity. We just have a much higher resistance at this point in the conductor. And then we show the end of the cable as an open circuit, where we show the reflection off of all remaining energy that's transmitted, can't go any further, reflects off the open and back to the time domain reflectometer. So we can kind of see that this technique, in essence, creates a electronic or graphical roadmap of the underground cable, showing different events along that path. The arc reflection technique basically takes the pulse echo technique and combines it along with a high voltage device, in essence a thumper. Now the reason why we're using a high voltage device is the pulse echo technique by itself is a very good tool for low voltage cable applications, signal control cables, telephony cables, data communication cables, maybe security system cabling. But we do face one problem when we're trying to use the pulse echo technique on medium voltage electrical power cables. Again, these vented trees that form a hole in the insulation, typically these type of faults require a breakdown voltage. The pulse echo tool by itself is very low voltage in nature. So if the fault requires some level of breakdown voltage, the low voltage pulse echo energy will in essence travel straight past the fault, never seeing it, and what we will see is just the reflection of energy off of the terminating event or the end of the cable. But if we apply a high voltage breakdown surge at the same time that we're sending the pulse echo pulses, when the fault breaks down due to the high voltage surge, or in essence when the arc jumps through the faulted insulation, creating an arc across the cable, the pulse echo wave will reflect off of that arc, hence the name arc reflection. Now, to see how this technique works, we are actually here taking two separate pulse echo pictures of the cable. The first, shown by the black waveform that was on the screen before, we saw show the end of the cable. We then sent a high voltage surge from the thumper along with the pulse echo surge, and the second waveform, or the red waveform, showed a negative reflection, which was the pulse reflecting off of the arc caused by the thumper. Fault, and let's get it back up there again. End of cable, and then fault as a result of the high voltage surge. So that would be an example of how the arc reflection technique works. On the next part of the presentation, we're going to go and look at each technique a little bit deeper, and we're going to talk a little bit about exactly how that technique is performed, the advantages and the limitations of the technique, and based on those limitations, what recommendation or other technique could be used to overcome those limitations. Capacitive discharge, or thumping, was first commercialized in the late 1940s by the James G. Biddle Company. The technique is highly accurate, but inefficient and potentially harmful if misused. The classic fault locating process has been to perform the capacitive discharge technique by connecting a surge generator, or thumper, to a faulted cable, and then walk back and forth along the cable path until a thump indicating the fault is heard. This process pinpoints the fault, allowing a repair crew to dig a hole and repair the faulted cable. In some cases, it may take hours or even days to walk the cable and definitely locate the fault. During that time, the cable is exposed to high voltage surges. A few years after polyethylene cable began to be installed underground, evidence began to surface that due to the aging effects of treeing in the cable insulation, high voltage surging for long periods of time was doing more harm than good, leading to a higher rate of repeat failures on these service-age cables. The same is not necessarily true for the paper insulated lead covered cables, where typically higher voltages and more energy is required to locate faults with no notable damage to the cable. There's mixed opinions on the triggering effects in the EPR cables. But thumping has been around for quite a long time, and today is still one of the more popular or readily utilized cable fault locating techniques. And we're going to take a look and examine it a little bit closer. Now first, the capacitive discharge or surge generator is not a very complicated device. As we can see in the schematic here, basically we have a power supply which in essence charges a large capacitor. This capacitor will store this charge until a discharge mechanism or switch is closed, at which time all energy will be discharged into the faulted cable. Now, when this traveling wave, a high voltage surge, encounters the gap representing the fault in the insulation, that energy will discharge through the gap and will in essence be taken up as a fault current traveling back to the surge generator, and then typically through discharge resistor network to earth. But this discharging of energy through this gap is in essence what causes the small explosion or the acoustic wave that travels up to the surface of the ground. But again, the surge generator, a relatively simplistic device in concept. Power supply, capacitor, charged potential, closing of the switch, discharging of energy with the intent of breaking down the gap or fault. Now, with such a simple device, there are a wide variety of surge generators on the marketplace, ranging anywhere from 50 pounds in size up to several hundred pounds. So what makes one surge generator or thumper different from the other? Well, selecting a surge generator in many ways is the same as selecting a hammer. Hammers, like surge generators, come in various sizes for different applications. If selecting a hammer, you need to look at the type of nail that you intend to be driving. Is it a finishing nail? Is it a railroad spike? Is it a framing nail? If selecting a surge generator, you need to basically look at the cable type that you intend to be surging or thumping on. You need to be taking a look at the overall length of the cable. Since cables are very capacitive, the longer the cable run, the more capacitance you are being loaded down with your surge generator. The typical layout, is this a loop circuit? Is it a radial run? Is it a branch network? Again, these will answer questions as far as what is the overall total capacitive load being put on my surge generator. And performance of a surge generator is based upon its output voltage and its energy capability. The larger the value of capacitance within the surge generator, the greater the amount of available energy for discharge into the fault. The greater the probability of intersecting the characteristic flashover curve that we're going to talk about a little bit later, which is characteristic to a gap or in essence a fault. And the output of the surge generator, as I mentioned, is output voltage and energy. Energy can be calculated, or energy can be found, if we know what the internal capacitor of the surge generator is and the applied voltage. Basically, energy will equal the capacitance of the thumper divided in half, multiplied by the applied voltage squared. That will in essence give us energy measured in watt seconds or joules of energy. Now, the graph that we show here looks a little bit intimidating, but to break it down, basically, if we were to model or profile a fault represented by this gap, a physical hole or gap between the conductor and the neutral or sheath of the cable. If we were to profile this gap over a range of voltages and time, basically what we would see is a plot similar to this red curve here. And this is what we call the typical flashover characteristics of a gap. what we can see is that in order to establish an arc or enable to break down this gap and discharge energy across it, we need a minimum of breakdown voltage. Okay, how much voltage can this gap sustain before its insulating properties or the remaining air properties or contaminating properties break down and we conduct straight through it? So one is, what is the minimum breakdown voltage? The other aspect that we discover with every typical flashover characteristic is there is a minimum amount of time that voltage must be present before this gap will flash over. Now that minimum amount of time is going to vary from fault to fault to fault, and parameters that can affect that minimum amount of time can be contamination. It could be the overall capacitive load of the total combined cable network. But again, we need a minimum amount of voltage, and that voltage must be present long enough to cause this gap to flash over. Now, in the waveforms of A, B, and C, these are representing different outputs of different thumpers, or surge generators, if you will. In the output of surge generator or thumper A, we see that it has more than enough voltage applied to meet the minimum voltage requirement. So we have more than enough voltage. What we also see is that the voltage stays on the cable long enough, does not dissipate along the cable, so we have plenty of time that this voltage is present in order to meet the minimum time breakdown. Therefore, thumper A would be a successful tool. It would effectively break down the cable fault, where we see it intersecting the characteristic gap right here, and we would get a successful discharge of energy and a successful locate. Now, when we move to thumper B output, we see that thumper B has plenty of initial voltage, but perhaps the limitation that we have with thumper B in intersecting this characteristic curve is perhaps the capacitor inside this thumper is very small, and in essence we don't have enough energy to overcome the combined capacitance of the cable that we're feeding into. So what happens is, although we have enough initial voltage, that initial voltage dissipates or bleeds away very quickly as it's traveling along the cable. It does not have enough capacitance in itself or enough energy to overcome the capacitance of the cable, and we cannot meet the minimum time breakdown. So although we're sending plenty of voltage in, it doesn't sustain long enough to actually cause the gap to flash over. In essence, the output pulse of thumper B is inadequate to go ahead and cause discharge at the fault and fails. In thumper pulse C, what we're trying to represent there is higher energy being applied. So again, a larger capacitor possibly is being used inside this thumper. We apply the same amount of voltage as we did with thumper pulse B, but we have more capacitance inside the thumper, hence more energy being applied to the circuit, and we're able to both meet the voltage requirement of flashover, and more importantly, having higher energy, we are able to overcome the capacitive effect of the cable and losses associated. So we have plenty of time and voltage to intersect the characteristic breakdown curve. We successfully cause the arc to flash over, and we're able to successfully find the fault. Now, if you were able to follow along in those examples, that really depicts the major differences between one thumper and another. Again, size and weight are going to be very big considerations when taking a thumper out onto a job. But remember, sometimes with the smaller, lighter weight and portability, the sacrifice may be that it's a smaller capacitor being used inside of that thumper, and in essence is going to be then lower energy being able to be produced as a result of that smaller capacitor. So a small portable thumper, although very convenient, on some cable jobs not effective. It's just not a big enough hammer. Even though it has good output voltage capability, with the low capacitance, we cannot get enough energy to overcome the loading effects of the cable or to overcome the contamination properties of the fault and to be able to drive enough current through in order to get a good successful breakdown. Now, let's talk a little bit about energy versus voltage. To increase the acoustic discharge, the actual sound that we hear on the surface of the ground, the thump, thump sound, okay, to increase that acoustic discharge at the fault, energy is required. Now again, based on that formula that I had mentioned before, where energy equals the capacitance of the thumper divided in half, multiplied by the applied voltage squared, energy can be increased by either increasing the applied voltage, or it can be increased by increasing the capacitance inside the surge generator. Now, in the practical world, there are a lot of variables that are going to affect the sound level of the fault that we hear on the surface. But taking out some of the uncontrollable factors, such as, is the ground dry, is it wet, is it sandy and porous, is it compact and clay? In a practical world, approximately 300 to 400 joules of applied energy is the basic threshold for hearing an acoustic discharge at ground level with a thumper without using any type of electronic amplification or acoustic amplification devices. Now, if we're out looking for a fault and we're on the job for about an hour or so and we're not rendering results, typically we want to increase the odds. So we want to get a louder thump. Now, if the only control that is on that thumper to allow us to increase energy is basically increasing the voltage output, for instance, the capacitor inside is fixed, we have no control over that, then we must increase the voltage in order to get more sound or more energy. Other thumpers will actually give us the ability to adjust or to change the capacitance value inside. Set a higher capacitance when we're using lower thumper voltages, set a medium capacitance value or a low capacitance value, so that we're able to get the best of both worlds. Low voltage in order to reduce stress, but still maximum energy in order to produce higher acoustic signals at the fault, and also to overcome capacitive loading of a cable. Now, the curves that I show here, if you know what the internal capacitance is of the thumper that you're using, you could actually compute these curves on your own by using that same formula, capacitance of the thumper divided by 2, multiplied by the applied voltage squared. And what we see is, in this sample, we have what we call a constant energy thumper. Now, a constant energy thumper basically is a thumper that gives you multiple ranges of output. And at these different output ranges, it's actually using different capacitive values. So for instance, in the example here, if we use the 0 to 8,000 volt range, we're using the maximum or largest capacitive setting inside of this thumper. So plugging in capacitance and voltage to the formula for energy, we obtain this curve, which will give me the energy level for any of my applied voltages. And what this shows is that if that minimum threshold of sound is approximately 300 to 400 joules of energy, what this tells me is to get 400 joules of energy with this large capacitive setting, I would need only to apply just a little bit over 3 kV, about 4 kV of voltage, in order to accomplish 400 joules of output energy. Now, if I were to reduce the capacitance, in order to get the same energy, Again, capacitance here is reduced, therefore I have to increase voltage in order to get to a higher energy level. So in this example, I would almost need to apply around 7 to 7.5 kV in order to get the same 400 joules of energy. What this has shown me is that if I had pre-tested this cable and discovered that it breaks down at a voltage level of less than 3,000 volts, I would be doing better by using the 0 to 8 kV thumping range, get higher energy at a much lower applied voltage. Okay, and that is the benefit of a constant energy style thumper. It allows me to maximize my output energy and to obtain the highest level of energy at the lowest possible thumping voltage. A progressive energy thumper is in essence a thumper that is designed with a single fixed capacitor. You have no control over the capacitance. The manufacturer sets it up where, I believe in this particular example, it was a 12 microfarad capacitor. So based on a 12 microfarad capacitor, a thumping voltage from 1 to 16,000 volts, this would be my energy discharge curve. In order to get to the higher energy levels, I can only accomplish this by going to higher and higher voltage levels. And remember, voltage is what causes stress to a surface age cable, not the energy. So, the advantages of the capacitive discharge technique is that it does require fairly minimum training. Now you'll need some safety training on how to properly handle the instrument, how to properly make connections, and how to set the various controls, but the capacitive discharge or thumping technique is very easy to learn and very accurate to do pinpointing. Basically, you walk along the surface until you hear the thump element emulating from the ground. Once you hear that thump and you can actually feel it on the sole of your shoe, you pretty much know that you are directly over the fault and you have the fault pinpointed. Now, the limitations of this technique, unfortunately, is that it's very time consuming. If you've got several thousand feet of cable, you better have a few of your friends along with you, and everybody strategically placed along the cable path. Therefore, everybody has a smaller physical area to survey listening for this thump. But even with a large crew, if you've got a lot of background distortion, like in a large industrial plant or out where the wind is blowing heavily and there's a lot of rustling of leaves or distortion in the background, you could walk over this fault several times in the course of a day without ever hearing it. So it is very time consuming. The fact that we're sending high voltage surges repeatedly out onto a surface age cable, we could be accelerating the channel growth of other vented trees that, had we not been thumping for so long, under natural aging, those trees may have lasted several more years of service life. But because of the constant voltage surging, we accelerated the growth of other weakened areas, and in essence, we are now setting the cable up for a future fault in the process of trying to find the fault that we're on today. So this technique, if used all by itself, can be potentially harmful. Also, the technique will not find faults that do not arc over. So for instance, if we have a dead short, what we call a bolted fault, where basically the conductor and neutral have come together and bonded, if there is no gap, there is no sound. No matter how much energy and voltage we discharge into the circuit, we have no discharge, we have no energy being discharged or jumped across. We just have basically a constant current loop. Now, so a bolted fault or a dead short, you can thump it all day long. You will not get the acoustic event you're looking for. You will not be able to pinpoint this fault. Again, in order to have sound, we need a gap, we need air. If the gap is too large, for instance, the cable blew apart, and in the process of blowing apart, let's say maybe the conductor had burned back into the dielectric material, or the neutral has burned back, causing a sizable distance in that gap. We may apply a large voltage to it, but we physically have too large of a gap to actually arc across. Now our choices here may be a burn down technique where we burn away insulation resistance to reduce the gap size in order to get the thumper to discharge and arc across properly. But again, this is going to come with stress to the cable. A very good technique that complements the thumper or capacitive discharge technique is when we use pulse echo. Pulse echo is excellent at finding hardened faults like a dead short circuit or a bolted fault. A pulse echo technique would be ideal for finding a blowout or an open conductor. So by utilizing pulse echo as a complement to the surge or thumping technique, we can also better our odds and reduce the amount of stress applied to the cables under test. Okay, the next technique that we're going to talk about is the pulse echo technique of the time domain reflectometry series. The technique of pulse echo transmits low voltage pulses of short time duration into a cable. The elapsed time of a transmitted pulse traveling the entire length of a cable and the pulse reflections produced by deviations from the harmonious structure of the cable are shown on a screen. Any reflections resulting from mismatches in the characteristic impedance of the cable, these mismatches may be caused by the start of the cable, splices in the cable, transformers, faults, etc. These reflections are then shown in a time sequence. So when you see the graphic display on a time domain reflectometer, the first event is the pulse or the start of the cable, and then the first mismatch impedance, second mismatch impedance, etc. Everything shown in a time domain format. Instruments performing the pulse echo technique, typically referred to as time domain reflectometers, make it possible to see into a cable and thus giving us the ability to visualize or detect or see different cable landmarks such as splices, transformers, cable transition areas, for instance like burial cable to aerial transition, etc. In addition to this, it also gives us the ability to locate the start and end of a cable, actually be able to take measurements of cable length, and also the pulse echo technique is ideal for locating faults that are in series with the cable transmission path, such as a broken or open conductor or neutral, or severe corrosion building up on a concentric neutral can be found quite easily with a pulse echo technique. Separated splices or sealed off cable ends, etc. could be found relatively easily with a time domain reflectometer or pulse echo technique. To a lesser extent, the pulse echo technique can be used to locate shunt cable faults or faults in the dielectric material in the cable. Again, the pulse echo technique can be used for this to a lesser extent, provided that the resistance of the insulation fault is a value less than 10 times the characteristic impedance of the cable being viewed. Now, it is not possible to locate with pulse echo all by itself a shunt or dielectric fault where the resistance is of values of 10 times or greater the characteristic impedance of the cable. Auxiliary equipment and techniques are available to convert high resistance shunt faults and intermittent shunt faults temporarily into low resistance faults that can be located using a time domain reflectometer technique. And as this presentation moves forward, we're going to be examining those techniques and how to be able to get more out of the pulse echo than just using it to find series related faults. But again, just an example of how the pulse echo works. We transmit and then we receive reflections. And the events are laid out in a time domain format. Now, we say mismatches to characteristic impedance. Basically what this means is, let's consider this top line to be the conductor of the cable that we're testing, whether it's aluminum or whether it is copper. That metal is going to have a very tiny amount of resistance per foot. Okay? Now, this bottom line, let's refer to that as the concentric neutral or the shield of the cable. Again, the copper and or potentially aluminum that's being used is going to have resistance, metallic resistance. So metallic resistance of conductor and neutral are part of the impedance parameters. When we place two metal objects in parallel with one another and we apply a voltage across it, we also create an inductance or an inductive field. So again, part of the characteristic impedance is inductance. Now, inductance is typically controlled by the spacing, the distance between the two pieces of metal. Now, in a cable, that spacing between the conductor and the neutral is fixed based upon the wall thickness of the insulation or the dielectric material. Okay? When we go through a transition like into a splice or a switch box or something, inductance will be changing because the physical separation of the conductor and neutral will be increasing as we go into a splice or as we go into a switch cabinet, etc. Now, we take two pieces of metal, we place them in parallel with one another. We basically have built ourselves a capacitor. So another fundamental property of cable and cable impedance is capacitance. And finally, the insulation resistance value of the dielectric material. So all of these parameters together basically is what we refer to as the characteristic or impedance of the cable under test. And the pulse echo technique, in essence, will allow us to find changes in any of these inherent parameters. Now, when we are looking at mismatches or reflections, there are two types of reflections that we, in essence, encounter, positive and negative. Positive reflections are caused by increases in the impedance. Now, an increased impedance is going to result from increases in metallic resistance or increases in inductance. These are going to cause an increase of overall impedance and, in essence, will cause a positive reflecting image. Negative reflections are going to be caused by decreases in impedance. Now, decreases are going to result from changes to the capacitance of the cable and decreases in the insulation resistance value of the cable. So, again, just to kind of recap, resistive and inductive changes cause positive reflections. Capacitive and insulation resistance changes causes negative reflections. So, not only does this pulse echo technique allow us to see into a cable and to see events, but based upon whether the reflection is in a positive or in a negative orientation, we also can interpret the type of change that we're seeing. For instance, a small positive reflected area might be a splice that's pulling apart, might be an area of concentrated corrosion on the neutral where we're adding resistance to the neutral value. Another area where we're seeing a small negative reflection might be an area of advanced water ingress or water saturation or treeing in the cable insulation. Could be a partial short circuit that we're seeing. So again, whether it's positive or negative, we can also make a little bit of an interpretation of what is causing that event. Now, one of the things I like about the pulse echo technique, these images are very repetitive. These reflected patterns are very repetitive. And after using the pulse echo technique for a little bit of time, you start to get used to and recognize these different patterns. Now, it doesn't matter whether I'm testing a telephone cable today and a medium voltage electrical power cable tomorrow, an open circuit is always going to look the same. whether it's an open conductor on a telephone wire or an open conductor on an electrical power cable. An open is always going to be a large positive reflected image. Short circuits, wherever I have two conductors touching or a conductor and a neutral touching, again, it doesn't matter what type of cable it is, a short circuit is always going to look the same. A splice, where I physically join two pieces of cable together. Basically what I'm seeing here is as the TDR pulse enters the splice, the conductor and neutral are separating, causing a very small inductive change, thus causing a very small positive reflection as the pulse echo pulse enters the splice. As the pulse echo pulse leaves the splice, the conductor and neutral are coming back together into the natural distance of the wall thickness of the dielectric material, but the two pieces of metal are coming back together, which is causing a capacitive change, and this in essence then causes a small negative reflection. So a splice is fundamentally no more than the reflection of the TDR pulse entering the splice and exiting the splice. And again, since it should be a proportional the amount of separation that we're pulling apart going into the splice and how much we're coming back together. If the splice is well constructed, there's no source of water ingress or anything in it, this pattern should be somewhat symmetrical. The up and the down should be somewhat symmetrical to one another. If we start to see a splice pattern where we start to see a lot of negative at the tail end of it, basically this says, well, here I'm seeing the conductor and neutral separating as I enter the splice. I've got the conductor and neutral coming back together, but I also have something other influence, which is further changing capacitance or further lowering insulation resistance value. Normally, this type of pattern is going to be caused by water getting into that splice and saturating into the splice. By the same respect, if the conductors are starting to pull apart out of splice, what we start to see is an increasing growth of insulation, or excuse me, of metallic resistance at the splice. So again, the up followed by down pattern typically is a splice. If it's bottom heavy, we can normally blame it on water. If it's top heavy, we can normally blame it on either corrosion or the actual conductor starting to pull apart. A distribution transformer on a residential loop circuit would be an up followed by a down, but normally we see a little bit sharper of the tips as we transmit through a transformer. If we have a branch circuit, and a branch circuit basically if we have kind of a main feed cable and then it either T's or Y's off. This, although it is a splice, it is a slightly different type of splice. Here we see a large additional capacitive value where it physically joins into the main trunk cable. So since capacitive changes cause these negative reflections, a T or a Y actually shows up more on the pulse echo as kind of a negative check mark looking image. But again, after viewing it these a few times on the TDR, you start to get used to these patterns. Water ingress typically are negative reflections because remember, water is going to change capacitive property, water is going to decrease the insulation resistance, but they're going to be very random. We're not going to have evenly dispersed water throughout the dielectric, so they're going to be random negative patterns that start to materialize over time. How we actually make measurements on a time domain reflectometer? Well, by measuring time. The time domain reflectometer will actually measure the amount of time it takes a pulse to launch out onto a cable, and then it will start to measure the elapsed time to when those reflections start to come back in. Now, if we know the amount of time that a pulse takes to leave and to return, we could divide that overall time in half because we're really not concerned with the round trip, we're only concerned with the outgoing journey. So what the time domain reflectometer will do is it will take the total time divided by half, and then it will multiply that by the speed at which the pulse is traveling. So I have the time it took to leave and to return, divide that in half, multiply by the speed it's traveling, boom, I've got distance to where the pulse traveled. So again, we launch the pulse, we start the timer, and we start to clock in the reflections. We measure the elapsed times, multiply by the speeds, and we're able to determine distances to events. Now, a very critical element or critical setting on a time domain reflectometer is this thing called velocity of propagation. Velocity of propagation is the speed at which these high frequency pulses are traveling on any given cable. And the speed at which these pulses travel will be influenced by the type of dielectric material and the thickness or the cross-sectional geometry of the cable. Kind of a little bit of a Mr. Science experiment that you can kind of visualize is if I took two jars, filled them up with two liquids of different viscosities, for instance, fill one jar with water, fill one jar with honey. If I drop a ball of equal size and weight into both jars, the ball that goes through the honey is going to travel at a much slower velocity than the ball traveling through the water. Okay. Very similarly, let's say that the jar containing the water is cross-linked polyethylene, and the jar containing honey is paper insulated, lead covered. Okay. The electrical signals are going to travel at different velocities over these different cable structures. Now, in the instruction manuals that come with the test equipment, also as on-screen help functions in many of the pieces of test equipment today, the manufacturers provide you a reference table of common values that you will see for different type of cable types. And the way we see these tables is it'll first show us the insulation type. For instance, in this example, a cross-linked polyethylene cable, kV size 15 kV, 1/0 wire size, and a velocity of propagation or VP percentage of 51. What that basically is we know how fast the pulses would travel in a perfect vacuum. They would travel at the speed of light, which would be 984 feet per microsecond, or 300 meters per microsecond. But we're not traveling through a vacuum here. We're traveling through the cross-linked polyethylene with a cross-sectional geometry 1/0 sizing. So the pulse is going to be slowed down. A velocity of propagation percentage of 51, in essence, means nothing more than the pulse is going to travel at 51% the speed of light. Okay? So we're going to be traveling at 51% of 984 feet per microsecond, or 502 feet per microsecond is the speed at which we'll be traveling through that style cable. So if you know the type of cable that you're going to be testing, you can look up the velocity of propagation in this reference chart that's provided with these pieces of test equipment, and you can start making accurate measurements of distance. But what if you don't know the velocity of propagation? Or let's say we have a transitional splice where, for instance, we have cross-linked polyethylene and it's now being spliced onto an EPR, or ethylene propylene rubber cable. Two different velocities. How do we get a good velocity of propagation for the overall cable and able to make accurate measurements? Well, another technique or trick that you can use is when you're viewing the cable on the pulse echo device, if you can find the end of the cable, okay, and sometimes you can validate that you're looking at the end by first have the end terminated as an open. You should be seeing a positive reflection. Then have one of your crew members at the other end put a ground onto the end. And while viewing it on the time domain reflectometer, when he grounds the end of the cable, if it inverts and goes to a negative reflection indicating a short circuit or ground, you know you're looking at the end of the cable at this point. Now, if you know the length of the cable, what you can do is you can place your display marker at that physical event, adjust your velocity value until the instrument reads the expected length. What we're basically saying here is this is simply a computer and a simple equation that's being applied in the computer. As long as I can give it two pieces of data, it can calculate an answer for me. So if I know the velocity of the cable, it can calculate length. If I know the length, it can calculate the velocity. Again, I can visibly see the end, I can place my marker there. I then simply adjust velocity until I read proper length. Now, let's assume we know nothing about this cable. I don't know a good velocity to use. I'm really not sure of overall total length and everything on the circuit. I can still get very accurate results using a time domain reflectometer by simply taking advantage of the fact that the cable has two ends. Now, if I enter in the wrong velocity value when I'm making my measurement, the time domain reflectometer is not going to know it's making a mistake. And I can use that as my advantage. Basically, what I'm going to do is I'm going to measure the distance to the fault from both ends, but I'm going to use the same velocity value. So, if I had the velocity value set too low, when I measure the distance from end A, I'm going to wheel out the distance, I'm going to put a flag on the ground, for instance, and then I'm going to repeat the same thing from end B. I'm going to use the same velocity, measure from the other end, walk it out, put a flag on the ground. If the velocity was set too low, I will undershoot the fault from both sides. The true fault location is going to be between my two markers. If the velocity was set too high, I'm going to overshoot the fault from both sides. Once again, I've bracketed out the true fault location. The fault is going to be between my markers. So here, even with knowing very little about the cable, not knowing the best velocity value to use, not necessarily knowing true total length, by simply doing bidirectional measurements, I can take 3 miles of cable and reduce it down to maybe a 30-40 foot area to where the true fault is going to reside. And I very quickly took a huge cable down to a very small section that I'll need to probe further in my pinpointing. Now, advantages of the pulse echo technique: it is relatively easy and it is fast fault finding. Reason why it is fast is you are viewing events on the time domain reflectometer screen. I don't have to be walking along the cable path tracking and looking for this fault. I can very quickly hook up the pulse echo, send in my pulse echo or radar pulses as they're referred to, and very quickly see the reflections on the screen and make measurements to those points. I can very quickly take a mile or two of cable and very quickly say, I have an event at 480 feet. I have an event at 2,300 feet. So again, it's relatively fast fault finding. All the time I'm using safe low voltage pulses. So I'm not stressing the cable. There's no electrical hazard to me in handling or using the time domain reflectometer. So it's good, safe, low voltage. I can use the time domain reflectometer anywhere from telephony cables, datacom cables, signaling and control, all the way up through low voltage, medium voltage, and high voltage electrical power cables. The pulse echo signatures or captured signatures that we obtain, we could actually use these for diagnostic values. For instance, if it was a three-phase circuit and we wanted to examine the splices, we could actually capture all three phases, overlay them together, and examine subtle issues that may be occurring on one phase that's not occurring on another phase. So again, I can use these signatures for archiving, trending, or diagnostic type purposes. Now, the limitations, though, of the pulse echo technique is traces that result from complex circuits. For instance, if I've got 5, 6, 10 T's or Y connections on there, all of these reflections can start to overlay one another, and the waveform can be very complicated. And it may be very difficult for me to be able to interpret or make meaning of all the reflections that I'm seeing. Well, in this situation, recommended practice would be to use what they call a differential technique or differential pulse echo. Basically, take a picture of a good cable phase and then take a picture of the faulted cable phase. Everything that is common, all the areas where they share common T connections, Y connections, transitions, etc., all these images will be the same. So we take the two data points from these two waveforms and we cancel them. So subtract out everything that's common and merely show us what is the difference. Show us only those reflections that are of difference. That will basically take us to the point of difference or potential fault on the bad phase. So again, we can take complicated waveforms by using differential techniques. We can go ahead and simplify them in order to more easily interpret our test results. Now, it is not possible to locate with pulse echo alone a dielectric fault or insulation fault where the resistance value is 10 times or greater the characteristic impedance of the cable that I'm measuring on. Now, the recommended technique or practice for this is the technique known as arc reflection. The next of the time domain reflectometer techniques that we're going to discuss is going to be that of arc reflection. The technique of arc reflection combines the capacitive discharge technique and the pulse echo technique for the purpose of locating high resistance shunt faults and intermittent shunt faults. A coupling device referred to as a filter or also referred to as a power separation unit is introduced into the circuit, allowing the high voltage surge generator and low voltage time domain reflectometer to be combined simultaneously to the faulted cable. The function of the surge generator is simply to transmit a high voltage surge into the faulted cable. This surge momentarily reduces the resistance of the shunt fault. During the high voltage impulse time interval, the pulse echo technique is applied using the time domain reflectometer. The momentary reduction in the shunt resistance established by the high voltage impulse or arc created at the fault will create a point of reflection for the low voltage pulse transmitted by the time domain reflectometer and thus allow us to see the fault. So as we can see on the example here, the red waveform was the pulse echo pattern taken before the impulse or thump. And what we were able to capture was the reflection from the end of the cable, but initially we could not see the fault due to the high resistance of the shunt fault. We then discharged the high energy or high voltage of the thumper into the conductor of the cable under test. When this high voltage impulse caused an arc at the fault, at that moment of time the fault became a short circuit, and we were able to reflect a pulse echo pulse off of that short circuit, and on the high voltage waveform we see the negative reflection indicating the flash point or the point of where the arc took place as a result of the high voltage thumper pulse. Now, breaking this down into more of a circuit model, what we have is the surge generator, as we discussed earlier in this presentation series. We have a power supply charging up an internal capacitor, and we have a discharge switch which in essence discharges the stored energy or voltage of the capacitor onto the cable under test. The next item we have is the arc reflection filter, and we have the faulted region of the cable, more importantly the gap. The high voltage surge that comes out of the surge generator has to go through the power separation unit. It is able to pass through the inductor but is blocked by the capacitor. The high frequency pulses of the time domain reflectometer are able to pass through the capacitor but are blocked by the inductor. Now, the sole purpose of the surge generator in this model is to provide breakdown potential to the gap. What we want to do is we want to reduce the resistance of this fault momentarily so that the cable analyzer or pulse echo can recognize or see the fault event. So the thumper merely creates the breakdown voltage. When the arc is established at the fault, at that moment of time, the impedance of the fault is 0 ohms. So we now take this second set of pulse echo pictures, we transmit again pulse echo pulse. During the period that the arc is on the cable, the resistance or impedance of the fault is 0 ohms. We bounce or reflect the pulse echo pulse off of that arc, and since it is a momentary short circuit, we have a momentary negative reflection that we see on the screen of the pulse echo device. Apologize, sounds like we're having some helicopter activity in the background. Now, the advantage of the arc reflection technique is any fault that will sustain an arc during the thumper pulse can be localized using the arc reflection technique. Now, even though we are using a surge generator, we have significantly reduced the amount of stress that is traditionally associated with the thumping technique. Because here, instead of just connecting the thumper and then starting to walk the line listening for the breakdown, what we're able to accomplish here is with the accompaniment of the pulse echo tool, we will only need 1 or 2 surges into the cable in order for the pulse echo to be able to find or see the fault and then display that image to us so we can make a measurement of distance. So what we've done here is we've greatly reduced the amount of stress by reducing the amount of surges or thumps it's going to take to find this overall fault. And the output of the thumper, the output voltage, is regulated by the arc reflection filter or power separation unit. So again, while we're doing this pre-locating technique, we are greatly reducing any high voltage stress to the service age cable that we're fault locating on. Now, the limitations to this technique: the traces, once again, if it's a complex circuit with many branches, T connections, Y connections, if we have a lot of reflections, the waveform can be difficult to interpret. But again, we can again apply a differential technique, called differential arc reflection. Basically, we start with the reference waveform. What does the cable look like under just standard low voltage pulse echo waveform? And then we capture that image and those data points to the time domain reflectometer. We then apply the high voltage surge to the cable. We create the arc or flashover, and we create a new waveform or a new TDR signature showing the reflection from the arc. Now, since we have these two waveforms, which are really just accumulation of data points, the computer or the analyzer will cancel everything common, getting rid of all of the unwanted reflections, and then very clearly showing us the point of difference or where the arc took place, allowing us to very quickly visualize and make a measurement to the flash point or reflection point of the arc. Now, long cables with very highly attenuating dielectrics or a lot of corrosion on the neutrals can very quickly absorb the reflected pulses of the pulse echo technique. And in essence, if the TDR or pulse echo doesn't have enough transmitted pulse energy to overcome these very long cables or high corrosion that's bleeding down the signal, we may not be able to see the end of the cable. We may not be able to see the actual fault event just because the signals attenuate before they get back to the receiver. So if we are dealing with very long cables with very highly attenuating dielectrics, or cables that have very severe neutral corrosion that again is just attenuating our pulse echo signals, a recommended technique in these situations would be the surge pulse reflection technique. Also, another limitation of pulse echo or time domain reflectometry is the arc reflection technique is greatly hampered when we use it on cables with fault current interrupters in the sheath or sheath gaps, or those cable circuits that use cross bonding. Also, these bonding techniques and current interrupters will greatly hamper the use of any of the time domain reflectometry techniques. But the next in our sequence that we'll move on to discuss is going to be the surge pulse reflection. Now, surge pulse reflection, again, we use the surge generator in order to create breakdown on the cable, or to create an arc at the cable fault. But what happens here is the device that we're using to view this is really going to be nothing more than an oscilloscope, which is coupled onto the circuit using a CT. Now, what happens and what we're seeing in this waveform is when the high voltage capacitor discharges, that discharge creates a current transient passing the internal CT, and we see that outgoing current transient on the oscilloscope. Now, when the cable fault actually flashes over, it's sort of like a thumper thumping back toward the test equipment. So at time period number 2, we see the returning transient caused by the arc established on the cable. Now, upon reaching the test equipment, that transient reaches the capacitor of the thumper, reflects again back toward the arc, and this continues to occur where this transient oscillates, or rings, if you will, back and forth between the arc and the thumper capacitor until all of the energy has been utilized or dissipated. So the resultant is a repetitive oscillatory waveform that kind of looks like a shock wave, or sometimes referred to as a sideways tornado. Now, since the reflection points is the thumper capacitor and the arc established by the fault, if we were to measure between any two consecutive peaks, in essence, we can determine distance between equipment and fault. The benefit of this technique is, even in a cable circuit with a lot of loss, since it is the thumper pulse that is creating the transient, as long as we have enough energy in our thumper to cause the arc, we will be able to pick up the transient and be able to make measurement to the flash or arc location using the surge pulse technique. Again, to break it down into the basic elements, we have the thumper. We charge up the thumper, close the switch. We get a surge potential that goes past the inductor, clocked in at time period number 1. The cable is energized, the fault flashes over and arcs, which returns a current transient back toward the equipment, which gets clocked in as it passes the inductor at time period number 2. And then this repeats as this transient oscillates between the thumper capacitor and the arc, causing a repetitive transient wave diminishing in amplitude as the energy is being dissipated. But if we measure between any two consecutive points, in essence, we've measured distance between the thumper and the fault. Here we see a basic transient. Again, this would be the outgoing thumper pulse. This would be the first arrival transient as a resultant of the arc or the fault. So thumper, fault, thumper, fault, thumper, fault, thumper. Measure between any 2 points. We determine distance between the thumper and the fault. The advantages of this technique is that with the surge pulse reflection, it's a very good backup to the arc reflection technique. In the event that the cable has a high degree of attenuation, whether it's due to corroded neutrals or whether it's due to a very long length of cable like submarine cables or very long cable runs associated with wind farming, and if we cannot get a pulse echo waveform to transmit these long distances, we're able to overcome that with the surge pulse technique or the impulse current technique, since really as long as we have a thumper with adequate energy to create the breakdown, we can capture the transient. Now, waveforms can be difficult to interpret even on simple circuits, so this technique normally does require a little bit of practice to become very good or proficient with interpreting or making your measurement points. There is a little bit greater error obtained in your distance measurements when compared to that of the arc reflection or traditional pulse echo techniques. But again, if we can very quickly take 5 miles of cable and reduce and localize the fault down to maybe 50 feet, we've done a significant value and reduction of time that it's going to take to find this fault. Once again, if we do have cross bonding or sheath gaps, like any of the time domain reflectometry techniques, this technique will also be hampered by the presence of sheath gaps or cross bonding.